Hello, good afternoon to you guys. My name is Carlo. I'm with Cartesi. And today I'm going to try to convince you to use our cool tech to do some interesting stuff. The name of this is Billions of Reasons to Use Cartesi, and I hope it becomes clear during the presentation. Well, okay. So today we'll be covering basically this quick overview of what Cartesi is, and then an intro into our tech, which is Cartesi rollups, its interfaces, a really simple application of how you can build a Cartesi application in this case in Python. And then I'll go through a couple of things that are being built with Cartesi and are nice things to inspire others. So this is just a preview. I'll come back to this later. But this is a really simple program in Cartesi. In this case, it's an echo application. Whatever you throw it throws back at you. And if you check the code on the right side, which is the whole application code, for the ones that are familiar with Python, this is just traditional Web2 Python code. There's nothing in there screaming Web3. You don't have to learn anything new. You're just using requests, which is a well-known HTTP client. So it's really easy for anyone used to Web2 to get started with Cartesi. But as I said, I'll go back to this later. So let's get started. So what's the idea behind Cartesi? So Cartesi started in 2017. Ethereum was booming at that time. And Ethereum is really nice. So we have all these decentralization properties, censorship resistance. No one can tamper with anything because if they try to, it's really hard. You have to lie with thousands of nodes in order to get it right. And it's awesome, but it comes with its disadvantages as well. So on Ethereum, everything is slow, is expensive, and it's cumbersome. Why? Slow because, well, you're sharing a single VM, all the resources with all the applications that are running on it. Expensive because you're always bidding for the resources that are scarce available in there. So you have to purchase that resources and overbid others trying to use it. And cumbersome because Ethereum was designed around the EVM, which is really good for sandboxing, make sure that no one's messing with someone else's computation. But it's not similar to anything that came before, so all the tooling has to be built from the ground up. So what's the idea behind Cartesi? What if we could have much more complex computations, still having these really cool guarantees that blockchain gives us, but with great tooling? And that's what we achieved. So what's our solution? So we have this really cool application-specific rollup solution. We basically do this rollup for each application that deploys on Cartesi. Each one of them has their own VM, and this VM is based on this RISC-V architecture, which is an open hardware processor. And since everyone's got their own processor, the applications are not competing for resources, and it's based on this traditional computation platform, well, we can boot Linux. And by booting Linux, we bring all the Web2 goodies for Web3 development. You don't have to learn Solidity to have all this really steep curve for doing your decentralized application. You can just use what you're used to and want to. And in order to make it easier for people to onboard, we wrapped all the complexity of the framework on an HTTP interface. So how do we achieve this? This is achieved by using a very cool dispute resolution protocol that secures this computation. It's based on something called verification game. I'm not gonna get really down on the details of how it works. Anyone interested on that can talk later to me. But basically what happens is that all these computations, they happen in the Cartesi machine. The Cartesi machine is deterministic. So if someone disagrees about the computation, they engage on this verification game protocol. We settle what's the first point of the computation you don't agree. And that single instruction is arbitrated by the underlying chain on a copy of the Cartesi machine implemented in Solidity. So when you have a dispute, it's the entire blockchain you're using underlying that's actually arbitrating if you're right or wrong. So it's very safe. Our security guarantee is that a single party willing to enforce the correct result is enough to guarantee it. Okay, just being a bit graphical here. So Ethereum tooling is really scarce because, as I said, EVM is not compatible with anything that came before. So everything is being built from ground up. And when you come to Cartesi, oh, well, you have everything you're used to on Web2. So you can use all the libraries, all the services, all the languages that you're used to. This is just a quick overview of how you can make your Cartesi machine drive, in which contains your application, everything you're going to use. So when you're building your Cartesi machine, you can take advantage of a Docker container, which uses Camel to emulate RISC-V, and all the Linux distros that are already built for it. And you just use whatever you want to install your environment. So in this case here, I'm just running from this RISC-V build of Slim Jammy for Python, which is a Ubuntu distro. You can use whatever you want. Alpine is your cup of tea, go for it. You want to use vanilla Linux, go for it as well. Whatever you want, you can start in there. Since I'm Ubuntu, and I want to use a SQLite database, well, I just apt install it, and it's available inside the machine for my usage. Then I just copy that directory in there to this opt Cartesi dApp, because on my directory I will have the actual Python files for this application, which actually has my logic, and I can just pip install the dependencies like I would do on any Linux machine. So for a Web2 developer, this is all very simple if you're used to Docker. Now let's talk a bit about the computational scalability. So if you take a look at V4Scan or whatever your source, you can take a look that Ethereum blocks, they generally have like 30 million gas on all the transactions within it. So considering you have the entire block just for yourself and you're doing the cheapest possible useful computation, so if you take a look at the Ethereum open codes, the cheapest one is adding, and that costs 3 gas. So that gives you a boundary of about 10 million instructions for the most you can do on an Ethereum block, considering you have the entire block for yourself, which is something really hard to get. Okay. Just as a comparison, this is hard to read, I guess. But in here I have a terminal, and in this terminal, I'm just booting the Cartesi machine and halting it, doing nothing, just booting Linux and just shutting down. And this is using alone about 37 million RISC-V CPU cycles, which are much more complex than just adding. So if you do equivalent operations on the EVM, it's not going to cost 3 gas, it's going to cost way more. But that's just to give you an idea of the scale of the computation you can do. And booting Linux and shutting down, which takes about 37 million RISC-V CPU instructions, happens in a laptop in 0.2 seconds, so it's pretty fast. Now just another comparison. I've done some dumb computation here using a shell script, and that took 3.7 billion CPU instructions, okay? And on a regular laptop, that took about 13 seconds, which is the average block time of Ethereum. So just to have a perspective of how that is compared to those 30 million instructions you can have in a Ethereum block, it's this grid. So the left top corner is a yellow square, and that would be 30 million instructions. And then 3.7 billion instructions will be all this blue grid. And that's not the limit of Cartesi machine computation. I just limit it to 13 seconds, but you can actually have as large computations as you want. Remembering that this machine is just for application, it's not shared among everyone, just like in Ethereum. So let's get started on Cartesi rollups. This is the overview of a Cartesi rollups application. So on the client side, traditionally you're going to do a web application. So you'll probably be using HTML, CSS, JavaScript, some framework you're used to, like Angular, React, or Vue.js, or whatever your capacity is. And then you need a couple of libraries to connect to the Cartesi framework. The Cartesi framework has 3 interfaces you're going to use. The first one is the JSON RPC one. And why is that? Because our framework is deployed on top of an EVM blockchain. And in order to provide inputs to the Cartesi machine, there's a data availability problem. So we force this to go through the blockchain for a special smart contract code framework. And well, to talk to Ethereum or any other blockchain, you generally do this using a JSON RPC interface into an Ethereum or Polygon or Gnosis or whatever you do in Node. Then we have an HTTP request API that's used for something like Ethereum calls. So it's ethereal calls you do to check some machine state that doesn't really do anything. It's a read-only operation, right? And finally, we have a further interface, which is a graphical one, in which you can create a Cartesi node for events and things that you emitted on your logic. Now, your decentralized logic actually resides inside the Cartesi machine. And in order to make it easy for you to program, we have this HTTP dispatcher component that wraps up the entire framework complexity on this simple HTTP interface. What does it look like? Well, let's go back to that first slide. Now let's go in details. So if you take a look at this code, we just start like our traditional Python program. We're importing requests, which is our HTTP library. We're importing the environment module from OS because we want to read the environment variable. In this case, it's being used on line 4 because we're looking at this rollup HTTP server URL, which is an environment variable we set with the address of this HTTP dispatcher. Okay. Well, once we know it, we ask for it, what do we have to process? So the basic structure of a Cartesi program is an iterator in which you call this finish endpoint. And when you call it, you're doing two things. The first thing is you're putting a payload saying what happened with the previous thing you processed. Is it okay? Is it invalid? If it's okay, you return a status accept, saying it's fine, the Cartesi machine should advance to state, it's fine. If it's invalid, if it's something that will corrupt your application or anything like that, you can just reject it by returning a payload with status reject. Once that happens, the Cartesi machine halts and it's waiting for the next input. The next input comes, this call returns, and you get a response with the data of the next thing you should process. The payload itself is in a field called data, and then you have some useful metadata. One of them is message address, which is the sender address. You have the timestamp of the block in which you received it, and a couple of interesting things. On line 26 specifically, we're looking for this request type. This is a pretty simple usage. It's just a metadata that can come with advanced state or inspect state, or lines 19 and 20. And that's for you to differentiate when you have an input that came through the blockchain that should advance your application state, or if that's ephemeral call, in which you just want to generate some state of the application, maybe for a front end to consume or something like this. So just an example, let's say you have a chess application. You move a piece, that changes your application state, that's going to come on an advanced state. Now you just open your application, you want to know if a game is going on or something like that. Traditionally, you would have to go through the blockchain, check all the transactions that you have to rebuild the application state, or use something like GraphQL to index the state and query it. With Cartesi, you can use this inspect state. You just provide your address, and it's going to return JSON, maybe with your chessboard configuration, and the player's turn, right? So this is the difference. In this really simple example, we handle either advanced and inspect states the same way. We just pick up the payload of the input, we put it on a JSON, and we emit an event with it. In case it's a handle advanced, we use our interface called notice, which is equivalent to an Ethereum event. And in case of handle inspect, we use the report, which is the wrapper for responses for this ephemeral call, which is the inspect API. Now on the left side, we're using a really simple front-end application we built in TypeScript that implements those three interfaces of the other slide. So if you call this command yarn start input send -- payload, whatever you put in there, and in this case hello there, it's the binary payload that's going to go on this add input framework, and it's going to be piped into the Cartesi machine. So that hello there, it's arising in here, false. And after we process this response, in line 8, that JSON with a notice, it's going to be posted with exactly that payload. So now if you call this front-end application with yarn start notice list, it will go to that GraphQL interface of the node, and it's going to say, hey, give me the notices, and you have a nice notice in there with the hello there, because this Echo application just pipes the input back to the output. So this is a really, really simple crash course on how to use Cartesi. It's a 27-line Python code. You can make it even less if you want. And it's just using HTTP interfaces, nothing fancy, nothing different. Cool. Now that you have a crash course on how to make a Cartesi application and the interface and stuff, let's take a look at some usages and some nice things people are doing with it. So generally, people use Cartesi either to further decentralize dApp logic, because most dApps you do when you go to high computation or something complex, you generally put a part of the dApp in smart contracts, and then you put most of the logic centralized. That works for games, for DAOs, for a lot of stuff. So with Cartesi, since you have a Linux machine with great tooling and a lot of computational power, you can actually decentralize this logic. express more complex logic because you got all the tooling, all the libraries, so you can have really complex mathematical functions that you just import and use. You can use NumPy, you can use data analytics, you can use machine learning, all the stuff that's already been developed, leveraging traditional stacks, and it's also way easier to onboard Web 2 developers into Web 3 because after all, they're using the tooling they're used to. So a first cool use case I want to show is this game. It's developed by a Taiwanese studio called Aferis, and the game name is Dazzle. It's basically a Pokemon and Candy Crush mashup. So you have your team, you attack the other one. Whenever you want to attack the other player, you do a combo on this shared puzzle, and then there's no problem about anyone needing to trust the server, about anyone tampering with the random number that's going to fuel the puzzle. So you're in a competitive match, you know that no one tampered with your board to get a better combo next turn, anything like that. The client itself is done in Unity. It's pretty beautiful. It's got some pretty nice effects, 3D characters that they use as NFTs. And the game logic they built in Rust and runs inside the Cartesi machine. So each match you can just run your own node, check it checks out, nothing was tampered with. If someone tries to tamper with it, you can just prove they're wrong and enforce the correct result. This is a nice DeFi application that was done inspired by the Mango hack on Solana. So there's this DeFi protocol landing in Solana that's really simple. And it was hacked by a guy that checked that they accepted a certain asset as collateral, and this asset had really poor liquidity. So this guy got something like $5 million, purchased the asset, pumped the price, goes to Mango, says, hey, I want 100 million USDT or another stablecoin, gets it because it just goes to a price oracle, checks out. But then if they try to liquidate it, it won't hold. It's not worth 100 million, it's worth those 5 million it paid. So inspired by this, these guys, they made this really nice risk analysis protocol called Nucleus. And well, they feed the Cartesi machine with prices and volumes of assets. And then they use NumPy to do some sophisticated analysis and come up with some robust metrics about liquidity and volatility. And then they give recommendations like, yeah, this asset is not good. You cannot liquidate over 10K on it. It's not going to hold. Or no, this is a great asset with liquidity, low volatility. You can liquidate $1 million and no issues here. This one is more machine learning and image processing. So this guy has this problem of people tampering with fingerprints. In many places in the world, it's used either for access, for clocking in and clocking out of work, this kind of stuff. And people mess with it. So they make fake silicone fingers to go in and go out, or to get access, or photocopying, this kind of stuff. What this guy did is he made this dApp in Cartesi, which is specialized on defining if a fingerprint was spoofed or not. How does it work? He gets inputs as a fingerprint image, then has a first C++ program using OpenCV. It processes this image and describes it in an array of features that is fed into a Python program with a really cool machine learning model he trained. And this model was trained to differentiate a real fingerprint from something spoofed from silicone or paper or anything like that. This one is more on games AI. This is from a guy that came from our community, and it's called Ultra Chess. So chess has this plague that people don't really play chess online. They open up a game, but they're not playing versus a human. They just open a computer game. Whatever you throw at them, they throw at the computer. Whatever clever move the computer does, they throw back at you. So this guy said, okay, so let's make it part of the game. You can play as a human, sure, but the main focus on Ultra Chess is actually you're a trainer of the bot that's gonna play. So you do your AI, you train it, you change its parameters, you put it in there, and then inside the Cartesi machine, automated matches happen, and you're king of the hill. You tune your bot, you defeat someone that previously defeated you. So it becomes a bot automated game, and the focus is on you training and improving your bot. Since it's happening inside the Cartesi machine, if you win or you lose a match, it's not because someone tampered with the match. There's nothing to tamper with. Anyone can reproduce all the matches and check that everything's fine. And in this case, he built it in Python and a web user interface. The bots themselves, they use a protocol that's established, and they can be developed in any language you want. So you can do a binary in C++ or Rust, or you can do a Python script or JavaScript or whatever you want. This one is a really cool application that came from India. So Indians, they have a problem with car insurances. Basically in there, you have an accident, you activate your insurance, and they deny you the payment. And why is that? They claim you're a bad driver. How do you dispute it? You go to justice. The decision is behind closed doors, and you cannot really dispute it. So what this guy's doing is a decentralized car insurance protocol. So most cars today, they have this OBDB2 port in which you can export all the data from the car computer. They feed it into the Cartesi machine. Then inside the Cartesi machine, they have this model that analyzes this data and come up with a risk metric saying you're a good driver, you're a bad driver, you're an average driver. And based on that data, they deny you or approve your insurance, and they make it cheaper or more expensive. So if your insurance is expensive or is denied or anything like that, you don't have to go behind a port or something. Well, you just check. The data is in there, the model is in there. Yeah, I'm a better driver. Or, no, I'm a good driver. They make a false claim, you dispute it, and you force a correct result. This one was also built in Python. This is a really nice application that was done in a Harvard hackathon. So these guys, they got this retro-style emulator called Ikemen Go that does games like Street Fighter. They put it inside a Cartesi machine. They make a Python program wrapping it. And they created all these crazy NFTs for Pikachu, Pokemon, Kung Fu guy, pizza delivery guy, you name it. And then this application called Colosseum, you have a betting phase. Everyone says, I think this guy's going to win, this guy's going to win. They all put their money. It ends. Then you have the automated match happening inside the Cartesi machine. And then you have the result and you pay the winners. Once you have the result, they also render the whole match into old school style video. So it's interesting. You bet, then you watch the match like you're watching MMA or something like that. And then you get your money in case you won. Once again, nothing to tamper with. If someone tampers with a fight, you just enforce the correct result by disputing a computation. And this is a really cool guy. These guys, they made this for a hackathon in Bogota. So NFTs have this problem in which NFT itself, it's not the assets you want. It's actually a certificate pointing to the asset. So there are a couple of cases in which you purchase this really expensive NFT and then the person changes that beautiful art for a blank canvas on the server or something like that. So these guys, they actually wanted to generate an NFT collection with provable art. How did they do it? Well, they generated the art within Cartesi machine. And in this case, they use a computation-intensive algorithm that generates fractals called Mandelbrot. They implemented it in Rust. So if you have an NFT from their collection and someone tries to tamper with the art or anything, you just go to the Cartesi machine and say, hey, this is not the real art. The real art is this one. This is a computation that generated it. Anyone can just verify this is the right art. This is a more traditional application, but still it's an interesting use case. So this is from a team of Poland. And what they did is they did a decentralized parking app. I'm not sure about your personal experience, but sometimes you get a fine for not paying your parking, but you were on time, all the stuff. You have to go through the common justice to dispute it. It's a hassle, especially if you're not from the place. Sometimes you don't know how to pay for the parking meter, all the stuff. So they make this really nice application. The front end is web in Vue, and they use Rust and Post SQLite on the backend. And they build this nice application in which you have the parking zones, you have the fees. You can just go in there and fill up your meter. Anyone can go in there and check that you're still on your time and do your thing. So it's a more traditional Web 2 application, made very easily inside the Cartesi machine. All these and many others, we have things with carbon credits. We have other things really interesting with machine learning. So sentiment analysis, all this stuff. They're available on this showcase page. We have our games. We have, some really nice projects in there. They're available in there. And just to inspire you guys a bit more on what you can do on Cartesi. So we have this track with a total price of 10K. The first winner is going to get a nice price of 7K. And then we also have a share pool for the runner-ups. So 3 teams share $1,000 each. Okay? So we had this Twitter in February of this guy asking, well, if Ethereum is really the world computer, can someone explain how no one has managed to get Doom working on it? And we had a very clever engineer in our emulator team, which said, challenge accepted. So yeah, he put Doom real-time running inside the Cartesi machine. And yeah, it's really cool. So if you look at his suite, I can give you the link later. There's a render of him playing. And there's also a GitHub repo for the courageous to use, because he hacked this really fast, so it's not really easy to reproduce it, but it's in there. Okay? And that's all. Thank you very, very much for your attention. I hope you learned something, maybe. And whatever doubt you have, you can shoot at me. We're going to be on our stand during the whole hackathon. So if you want to exchange an idea, if you have something you want to build, if you want to brainstorm, if you're trying to build with us and you have some problem, you need debugging or anything like that, we're there available for you. Thank you, guys. So I think we have some time for questions if anyone wants to ask something. Sure. How what's works on randomness? Okay. So the question is how randomness work, and that's a great question. So the way it works is when you generate a random number on a computer, it's not really random, it's pseudo-random, right? And the source of entropy in the Cartesi machine is controlled, otherwise it's not deterministic. So when you generate a random number in a Cartesi machine, it's always going to be the same because other people will reproduce it and it's the same. That doesn't mean you cannot have random numbers within it. How do you do it? There are multiple techniques and that depends on your application. So let's get Dazzle for example, which is a multiplayer game, right? You need to generate a random number to refill the board. The way you do it is you use a seed that's a joint number from both players in order for you to have both players contributing without one mining advantage random number. We use a scheme that's well known called commit and reveal. So basically one player commits to a number, maybe the hash of the number, the other player submits the actual number, and then the first player has to review the first number. And then it's a hash, so you hash the number he provided. If it checks out, that's a number. If it doesn't, he's trying to tamper with it. Everything's fine, combine both, you have a seed for a random number. That's a strategy. You can use our approaches. It depends on your application. You can, let's say you have a slot machine application, for instance. You can use something that's hard to control, like the block hash of the input that's coming, requesting number. You want to be maybe a little more safe. You can use Oracle from Chainlink. You can use a VRF. Yeah, there are many options. Yeah, because you can always reset the seed on the Linux system. So yeah, you just set the seed on the system and that's going to be used universal. Yeah. Cool. Anyone has got further questions? Okay, I guess that's it then. As I said, great hackathon for everyone. If you need us, want to trade a word or something, we'll be on our booth and happy to talk to you guys. Have a great evening.